3.9. I think what you'll find is that this problem looks really intimidating, but it's not quite as hard as you might expect because some cancellation and stuff happens when we take the derivatives. But let's run through this problem the same way that we ran through the last problem. See if we can make sense of all the concave ups, all the concave downs, all the increases, all the decreases. Okay, so we're going to start by increasing and decreasing. So to do this, I'm going to start with part A. I need to find the derivative. We did this derivative in 3.1, but in case you don't remember, we have to use a quotient rule to do this. So the derivative at the top is 2x times x squared plus 1 minus x squared times the derivative of the bottom, which is 2x, all divided by x squared plus 1 squared. This was one where if we do a little bit of simplifying first, it's going to make our life easier. So this becomes 2x times x squared, which is 2x cubed, plus 2x minus 2x cubed, all over x squared plus 1 squared. Now what's nice about this? This x cubed and that x cubed cancel, and we get just 2x divided by x squared plus 1 squared. Okay, so again, so there's a fair amount going on here, but the final answer ended up being not too unbearable because our goal now is to figure out where that thing equals 0. We need to ask, can it be not defined? Well, it could be if the denominator could ever equal 0, but notice the denominator could only equal 0 if x squared plus 1 equals 0. But that would mean that x squared is a negative 1, which would make x squared an irrational number. So this one, even though we have a fraction, we still don't get the does not exist. It still always exists. So at this point, we only need to figure out where this thing equals 0. So we need to have 2x over x squared plus 1 squared equals 0. And now, well, you can multiply by this denominator, but what you find is that really the only thing that matters is when that numerator equals 0. And so x equals 0 is the only point that shows up when you do this. So we only have one point on our number line. And our number line consists of just the point 0. And now all I have to do is I have to check points on the right and left of 0. And so all I have to do is I have to put, say, -1 and +1 into my function. So if I put -1, I get 2 times -1 over -1 squared plus 1 squared, but that ends up being 2, but okay, so this ends up being -2 divided by 1 plus 1 is 2 divided by 4, which is -1/2. So this is negative, so that means we're decreasing on this side. Now I put +1 into my equation and see what I get. When I put +1 into my equation, I get almost the exact same thing. This equals +1, which means I get 2 times 1 divided by 1 squared plus 1 squared. But now I get 2 over 4, which is +1/4. So I get positive, which means I'm increasing over here. So I'm ready to write my answer for part A. So for part A, let's move all these off. So for part A, my answer is that I'm increasing from 0 to infinity, and I'm decreasing from -infinity to 0. So I'm increasing on that whole side and decreasing on that whole side. So we can already kind of have some sort of picture of our graph. We know that we come down here and up here. Now, the rest of what happens is a little bit more confusing, so we'll have to be a little bit more careful. But that's the basic shape that's going on. So we get increasing and decreasing. And then I also know that since I'm increasing and decreasing, I have a local minimum at x equals 0. And I have no local max because there's no point at which it switches from increasing to decreasing. We only switch from decreasing to increasing. Okay, so that's a good start on the problem. Now we're ready so this was part B. So now we're ready to tackle part C and D. And to tackle part C, we need to come back to the derivative that we had. So for part D, we'll have f of x equals 2x divided by x squared plus 1 squared. And I need to now take, this is my derivative, and I now need to take a derivative of this derivative, which is a little bit of a mess, but I think we can do it. Okay, so we'll have f double prime of x. We need to do a quotient rule. So the derivative of the top is 2 times x squared plus 1 squared minus 2x times, now I have to take the derivative of the bottom, and oh, this is a mess because now I have a chain rule inside of a quotient rule. But guess what? You all have proven to me that you're very good at these derivatives. You just can't forget them. Okay, we've got a chain rule inside of a quotient rule. So the chain rule means the derivative of the inside is 2x, and the derivative of the outside, uh-oh, I need to give myself some more space. So let's start writing this again. 2 times x squared plus 1 squared minus 2x times the derivative of the inside, which is 2x, times the derivative of the outside, which is 2 x squared plus 1, all divided by x squared plus 1 squared squared, but that just means we have x squared plus 1 raised to the 4th power. Okay, this looks a little bad right now, but there's something we can do that makes our life quite a bit easier, and that is we can factor out one of these x squared plus 1s. So let's go ahead and do that before we start. So if I factor out an x squared plus 1, then I'm left with 2 x squared plus 1, because I've only got one of them. I factored one of them out, minus, and now notice here I got 1, 2, 3, 2, 4, 8. Now I've got 8 x squared there, all divided by x squared plus 1 to the 4th. Now I'm going to cancel out one of these x squared plus 1s, and I'll make that a cubed. And maybe my algebra will become a little bit friendlier. So let's keep going. I know there's a lot going on, but we got to keep going. And we'll get, this is equal to 2. I'm going to distribute, and I'm going to get 2x squared plus 2 minus 8x squared all over x squared plus 1 cubed, which is equal to, it looks like I get 2 minus 6 x squared all over x squared plus 1 cubed. All right, so now again, I need to ask, can this equal 0? And the answer is no. It could only equal 0 if x squared plus 1 is equal to 0, and that's my imaginary number. Or, I mean, not equal 0. Does this always exist? It can only not exist if I put an imaginary number. So this always exists, so I only have to solve the equation, does it equal 0? I'm going to multiply by the denominator and realize that my problem becomes 2 minus 6x squared equals 0. I'm going to just do a little bit of algebra. I'm going to put my negative 2 over here and divide by 6. Negative 2 x squared equals 1/3, and now I can see my answer staring at me. My answer is x equals plus or minus the square root of 1/3. So square root of 1/3 is about 0.577. So square root of 1/3 is what we get. So I'm ready for my number line now, for my second derivative number line. And I know this looks like a mess, but we're gonna keep going with it because, well, it's the only choice we've got. So here's my number line. My number line has only 2 points on it. It has negative square root of 1/3 and positive square root of 1/3. I could have put 0.577 in there instead. And then I have to plug them into my equation. And my equation that I'm plugging into is that derivative equation that I had earlier, which was 2 minus 6x squared over x squared plus 1 cubed. So I'm putting all my points in here. What points am I going to choose? Well, let's choose negative 1. That seems like a good starter point. 2 minus 6 times negative 1 squared over negative 1 squared plus 1 cubed. So it looks like I've got 2 minus 6, so it looks like I have a negative 4 on top, divided by 2 cubed, which is 8. So it looks like I get a negative 1/2. So it looks like this is negative, and I've got concave down on that section. Tell you what, I'm going to jump on over here and do positive 1 because I can see really quickly what's going to happen here. And if I do positive 1, it's the exact same things go in my equation, but I still have negative 1/4 and still have negative 1/2. So I have negative and concave down over here. Now the last thing I'm going to do is pick something in the middle of those two, and 0 sure looks like the best choice. So let's put 0 in my equation and see what I get. So 2 times 6 times 0 divided by 0 squared plus 1, and this looks like 2 over 1 cubed, which is a positive 2, and so this middle part here is positive, and so we get concave up. So we can see that our graph is now concave down here, concave up here, and concave down here. So we're now ready to make our equation. Maybe I should write down my answers. I don't know. Let's write our answers out for this problem, and then we'll come over here and start trying to graph it. So what are my answers? My answer for part C is that I'm concave up from negative square root of 1/3 to the square root of 1/3. If you use decimals here, that's perfectly fine. And I'm concave down. Sorry I'm lazy and never write concave up, concave down. You are probably okay with that. Concave down from negative infinity to negative square root of 1/3 and square root of 1/3 to infinity. So that's a good way to write that answer. Part D, do I have any inflection points? The answer is yes. You'll notice I have inflection point here where I switch from concave down to concave up, and an inflection point here where I switch from concave up to concave down. And I have 2 inflection points. My inflection points are at x equals negative square root of 1/3 and x equals positive square root of 1/3. If you wanted to say x equals plus or minus the square root of 1/3, I think you would be just fine with saying that. Okay, now all that's left is to come over and try to put our graph together. This graph is going to be a little bit easier to visualize than the last one because we don't have as much going on. All we've got is we've got a 0 on here, we've got a square root of 1/3 on here, and we've got a negative square root of 1/3 on here. So as I look at my pictures, what do I see? I see that at the 0 point is where it switched from increasing to decreasing. Is that right? Did I get the right numbers on here? Hold on. Oh, wait. No. Okay, I had those backwards. It switched from decreasing to increasing on that section. Okay, good. So I got where it switched from decreasing to increasing, and then for my concave up and concave down, what I saw was that it was concave down, concave up, and concave down. So as you start putting these things together, we can kind of see our picture. We're going down and we're going back up. So we kind of come down and come back up, but we don't do it in straight lines. We do it in this curvy way. We're here, we are concave down, so that means we kind of have that type of shape here. And then we have an inflection point and it bowls there. And then we have that type of shape here. And then we have an inflection point where it does that. Okay, there's one last question to figure out and by the way, I knew that it kind of hit 0, 0, because if I put 0 in my equation, I get 0 for an answer. So there's one kind of last thing to figure out, and that is what happens on these 2 endpoints. What's going on here and what's going on right here? Are they growing forever? Are they leveling out? What's going on those endpoints? That's going to be the section 3.4 question, and we're going to ask ourselves what's the trend in both directions. So we'll actually come back to this graph and make this graph look a lot neater at that point. All right. Well, I hope 3.3 goes well. I know it's a lot of work, but stick with it. We're going to definitely have some take-home problems on this, and I want you to feel really good about this because this is one of the big ideas in calculus. So stick with it, work hard, and come and see me.